right, so we're going to look at another application of derivatives today. Most of the questions that we've been doing up to this point in the semester have primarily had relationships with physics. And so calculus actually has applications beyond just the natural sciences. We often talk about chemistry, physics, there's even some relations with biology. But more recently in time, we've also started looking at applications for calculus in psychology, sociology, economics. Economics is a big one. A lot of people going into business are going to be doing calculus courses in relation to economics. Some ways that derivatives can be used in other sciences. Psychology, there's the theory out there about the learning curve, and so psychologists might actually make a graph of performance versus training time, and they'll actually want to be looking at the rate of performance with regards to time, and that would be the derivative. In sociology, sociologists might be analyzing the spread of rumors or fads or fashions, so they might look at a fraction of the population who knows a specific rumor with regards to time, and then the rate at which that rumor spreads would be the derivative. So the one we're going to look at today is economics. And so this is looking at things like cost, profit, revenue, and so on. So there's some terminology I need to introduce you to begin with here. Economics have some very specialized vocabulary that they use for rate of change with regards to derivatives. So first of all, there's sort of a general cost formula, and you certainly don't need to memorize this. This is just for any of you that are thinking about going into business. Certainly you'll get into much more detail with this when you are in college. But this would be sort of a standard formula for cost. So your cost with regards to x would be a plus bx plus cx squared plus dx cubed. A would represent your fixed costs, like your rent, maybe your building, your standard building expenses and whatnot. But that would be sort of your fixed cost, things that stay the same. And then your other terms would relate to labor, labor costs, other maybe overhead costs, and so on. I don't want to get into too much specifics because I don't actually have the background when it comes to economics. And again, you would get into much more detail with that when you are in college. So we're going to start off with an example here. The formula's already been defined. We've got the cost function in dollars, the revenue function, so the money we're bringing in, and then the profit. Profit is the difference between revenue and cost. So the money that we bring in would be our revenue, and the money that we spend would be our cost, and the difference between the two would be profit. And so we can have a net profit that's positive, or we can have a net profit that's negative, meaning we have a net loss. All right, so in this particular example, we've got the profit being the revenue minus the cost. We can actually go through and calculate what that would be. So x cubed minus x cubed would be 0. Negative 3 minus negative 6, so negative 3 plus 6 would be 3x squared. And then 12x minus 15x would be negative 3x. Okay, and then if we were working with profit, we could certainly go forward with that. We've looked at when we were doing other applications of derivatives, we were looking at average versus instantaneous. Well, average cost would be the change in cost divided by the change in the number of items, or C of x2 minus C of x1 all over x2 minus x1. So essentially what you're looking at is you're looking at the rate of change of cost. Marginal cost is what they talk about when we're talking about an instantaneous change. So instead of seeing instantaneous, you're going to see marginal. And so when we're looking at marginal cost, this will be the limit as the change in x approaches 0 of delta x over delta C over delta x, or we're looking at the derivative of cost with respect to the number of items, or the x. So marginal cost is the derivative of the cost function. So if we were to look back at our original examples up here, the cost function is given to us there. The marginal cost would be the derivative. The revenue is given to us up here, and the marginal revenue again would be the derivative. Now we'll get a little bit more detailed into detail in terms of what marginal cost is, but I'm going to show you that using an example. So the example we have here, it says a company is producing a new gaming station. Management estimates that the cost in dollars of producing one gaming station is given by that formula. And so the first question says, find the average cost per machine if producing 100 gaming stations. And so we have the cost of 100 gaming stations divided by the number of gaming stations. So subbing that in, we have 2,000 plus 100 times the 100 machines minus 0.1 times 100 squared, all divided by the 100 machines. So that gives us $1,000 divided by 100 machines, which works out to $110 per machine. Now, what if the company wanted to find out the actual cost to produce just one more gaming station? So the cost to produce the 101st gaming station. Well, that would be the cost to produce 101 machines minus the cost to produce 100 machines. And so if we set that up, the 101 machines would be 2,000 plus 100 times 101 minus 0.1 times 101 squared minus the cost for the 100 machines above, which we already know is $11,000. So if we sub all that in, that's $11,079.90 minus the $11,000 it costs to make 100 units, and that would be $79.90 for the 101st machine. So it costs us $110 per machine when we're making 100 machines. But if we want to make 101 machines, it's going to just cost us an extra $80 or $79.90. Well, what if we look at marginal cost? If you remember from the first page, marginal cost represents the derivative, okay, the first derivative. And so if we take the derivative of that cost formula, C prime of x, we get, the 2,000 cancels out, so we're going to have 100 minus 0.2x. And so if we sub in the 100 units, we get 100 minus 0.2 times 100, which gives us $80. So if you look at these two numbers, the $79.90 and the $80, these numbers are mighty close. And so if we want to look at a more detailed definition of marginal cost, the marginal cost of producing n units is approximately equal to the cost of producing just one more unit, or the n plus first unit. All right, we're going to look at one more example. An apple farmer currently has 156 trees yielding an average of 12 bushels per tree. The farmer is expanding his farm, and he's expanding at a rate of 13 trees per year. And with improved husbandry, he's improving that average annual yield by 1.5 bushels per tree. The question is, what is the current rate of increase? So current rate means, again, we're looking at instantaneous, so we're looking at that first derivative. What's the current rate of increase of his total annual production? So we need to know his total annual production. All right, so lots of information in that word problem. So let's break it down, look at what we're given, define some variables, and then see where we go from there. So the apple farmer is currently producing 156 trees, and he's yielding an average. So we're talking about the number of trees and the amount of our yield. So we're going to define our variables as n. So n of t, so we're talking about time, is the number of trees. And y is going to be our yield. So our yield per tree with respect to time, or as a function of time, so t years from now. So t being time. Okay. So if we use those as our variables, let's look back at the formula and see what we're given. Well, we're told there's 156 trees, so that's going to be n. We're told our yield is 12 bushels per year, so that's going to be our y. The farmer is expanding his farm at a rate, so now we're talking about derivative, a rate of 13 trees per year. That's related to our n, so our dn dt. And he's improving his yield, so he's improving his rate of yield at 1.5 bushels per year. Per tree, sorry. So that would be our dy dt. So if we write those down, N is 156 trees. So these are all the amounts that were given. Y is 12 bushels per year. Now, we're talking here at this point, this is at year 0. So that's the initial year. dn dt, so the rate of change of the number of trees is 13 trees per year. And dy dt, so the rate of change of yield per tree is 1.5 bushels per tree per year. Now, if we look at the last question, it says, what is the current rate of increase of his total annual production? Well, the production is going to be the number of trees times however much each tree produces. So our production will equal our number of trees times the yield per tree. In other words, P is going to equal N times Y. So before we even start plugging in numbers, we need to take the derivative because we're asked for the current rate. In other words, we want derivative. So we're doing implicit differentiation again. So dp dt equals N times 1 dy dt plus Y times 1 dn dt. And remember, we're using the product rule. So we're looking for that current change. We've got dp dt. This is what we're finding out. Our n we know is 156. Our dy dt is 1.5. Our y is 12, and dn dt is 13. So we put all of that information into our calculator, and we get 390 bushels per year. So his production is increasing by 390 bushels per year. So hopefully those couple examples give you an idea why calculus has such a valuable role when it comes to economics. There are some more examples in your textbook. If you want to check out pages 136 to 138, they're similar, but there's a little bit more explanation and some slight tweaks there that you might find valuable. So again, if you're looking for some more examples, I would check out your textbook. All right, have a great day, and we will see you next time.